backpropagation is the foundation for whole deep learning training. It's only one algorithm or one technique which appears in all the architectures in various forms, okay, various nuances and forms, but the basic idea is same: gradient descent, and applying gradient descent to change the weights. So feedforward network and backpropagation. We started discussing the feedforward network with the XOR example. And in the feedforward network, there are three kinds of neurons. The first kind is the input layer neurons, okay, which receive input. And for XOR, you see X1 and X2, they get values 0, 0, 0, 1, 1, 0, 1, 1. This set of neurons interact with the environment. They receive input. In the outermost layer, we have another set of neurons, which are called output neurons. But the power of the neural network comes from what is called the hidden layer neurons. Okay, they are not visible to the environment, but they assist in the computation. So can somebody tell me why hidden layer neurons increase the... Without hidden layer neurons, the power of the network is very minimal, equal to the power of the perceptron or a single neuron. Why do the hidden layer neurons, when employed in correct number, increase the power of the network? They increase the number of regions produced by intersection of hyperplanes. No, this was done in the class. So don't forget what is done in the class. So the number of the computing power increases because the number of regions produced by intersection of hyperplanes increases. Each neuron brings its own hyperplane. So hidden layer neurons increase the computing power. Now we had an interesting discussion on compositionality. The linearly non-separable function, XOR is a linearly non-separable function, is decomposed into three linearly separable functions to compute the non-linearly separable function. You compute x1, x2 bar in one of the hidden layer neurons, x1 bar, x2 in the other neuron, hidden layer neuron, and or in the outermost neuron. You can also compute x1 or x2 in one of the hidden layer neurons and x1, x2 bar, which is NAND of x1 and x2 in the other hidden layer neuron, and compute AND in the outermost neuron. So in your lab, one of the interesting tasks will be discovering what do the hidden layer neurons compute. So once you train this feedforward network, okay, the training algorithm is backpropagation, which I'll describe very soon. You should be able to find out what are the hidden layer neurons computing. Are they computing x1, x2 bar and x1 bar, x2 and the final neuron computing OR? Or is it that they are computing x1 plus x2, one of the neurons, and the other neuron is computing NAND, x1, x2 bar? This you will have to find out after backpropagation has succeeded in training the network for XOR. Okay, so this will be a consistent theme for all your backpropagation assignments, lab assignments. You will have to discover what the hidden layer neurons are doing. In today's deep learning based AI, what the hidden layer neurons are doing has a terminology. It's called probing. Okay, probing the deep learning network, probing a very deep network to see what the hidden layer neurons are doing. To give you an example from natural language processing, let's say you input a sentence in the input layer. Inputting a sentence means giving its representation and deciding whether the sentence has positive, negative, or neutral sentiment. And there are many layers in the hidden part of the network. which are not visible to us, but they're computing. So we then begin to probe. Maybe some of the neurons are finding out the adjectives in the sentence, because adjectives contribute to sentiment. Right? This movie was wonderful. Wonderful is the adjective, which is saying it's a positive sentiment sentence. Or this game was atrocious. Atrocious is a negative adjective. So maybe some of the neurons are devoting themselves to identifying adjectives and giving a signal that I have found a positive adjective or negative adjective, or I have not found any adjective at all. Okay. So what these hidden neurons do is a very important and interesting investigation, which you must do in your backpropagation network. Okay. So there will be assignments on linearly separable, non-linearly separable functions, and also some machine learning data. There you'll have to discover what the hidden layer neurons are doing. That is the non-trivial part of the assignment. Okay, fine. So the output neuron and the hidden layer neurons are also known as computation neurons, because they take the input, compute dot product of input with the weight, and then compare with threshold, and then give an output. So that's why output layer neurons and the hidden layer neurons are called computing neurons. Okay, the input neurons just receiving. That's all. So we have also said that this network in front of us is an example of complete and pure feedforward network. Complete because every neuron is connected to every neuron in the previous layer. Pure because there is no jumping of connection. You don't have a connection going from X2 to the straight away to the output layer. There is no bypassing of layers for the connection. And also this is feed forward. The input information flows forward. Okay, there is no backward connection from any layer to the previous layer. Okay, so this is, you can see it is a special kind of graph, okay, which the feed forward network represents. And also we must understand that since neurons are computing devices which are different from symbolic computation, they deal with numbers only. Okay. Of course, I understand that symbols also are represented inside the computer in terms of bits, 10 bits. So these deal with pure numbers, and these numbers are representations of the problem. Okay, so that's why in AI, a very important and basic question is how to represent the problem. Okay, so representation of the problem plays a very important role. And you might have encountered this or will encounter this notion of representation in the machine when you do, let's say, NP completeness theory, NP hardness theory, representation of the problem. Okay. So these are some of the basic facts about feedforward network. When I ask you questions in the lab about these basic points, there should not be any faltering. Okay, there should not be any mixing or confusing of issues. What is a pure feedforward network? No hesitation. Okay, you should be able to define them clearly. This is your first exposure to AI, and let's make sure that all the basic terminology definitions are completely clear. Any question on feedforward network? No, okay. Now we have a bit of a difficulty. Okay, let's see what the difficulty. So we have also defined error, which is called total sum square error. It takes neurons in the outermost layer and notes the observations. The setting is called supervised learning. The input-output pair is specified. Okay, so we were remarking on digit recognition feedforward network. So if we have a 8-segment display, then there are 8 neurons in the input layer. And there are 10 neurons in the output layer. Okay, so if the 8-segment display corresponds to 6, the 6th neuron, let's say from the right-hand side, will be on. Others will be 0. So it is mapping an input vector to an output vector. Okay, so what we do is that the output vectors and input vector pairs are given to us. These are called data instances. And given an input, I observe the output from the feedforward network, compare it with the target value, Ti minus Oi, and so that the errors don't cancel each other, we take their square. You might say that why not take mod? Mod will not work because we need derivatives. Okay, and mod is not a continuous function. Okay, so we take the square and sum the errors, and we do it for every neuron in the outermost layer, and we do it for every input-output pair. And then take a half, so that when we take derivative, this half and 2 cancels. This is called the total sum square error. Okay, a very popular error function. Equally popular is the cross entropy error function. Error is also called loss. When we pronounce error, we use the symbol E. A much more common symbol is L, okay, which corresponds to loss. We call it the loss function. An equally popular loss function is the cross entropy loss, which we'll see going forward. Cross entropy loss is used to compare 2 probability distributions. Sum square error is not good for comparing probability distributions because the numbers become very small. Okay, cross entropy function involves log, which is good for dealing with small numbers also. So cross entropy loss compares 2 probability distribution. If you're wondering why probability distribution, what has probability got to do with AI? Probability has got everything to do with AI, because AI computing systems power comes from dealing with uncertainty, and it is a requirement for AI systems to be able to deal with uncertainty. Okay, so here is the notation, and Ti is target output, Oi is observed output, I is the index going over n neurons in the outermost layer, J is the index going over P patterns, input-output patterns. And XOR has P equal to 4. There are 4 patterns, input-output pairs, and N is only 1. Now, key question is, how do we change the weights in the neurons, okay, which are entering the neurons or leaving neurons? How do we change those weights? One might be tempted to say, okay, why not use perceptron training algorithm? Take a failed vector and change the weight accordingly. Just add the failed vector, as we have seen in perceptron training algorithm. Will that work? Will PTA work? What do you say? Can we use perceptron training algorithm here? No answer? What does perceptron training algorithm depend on? Failed vector, failed. Okay, and how do we know whether a vector has failed or not? From the label. So when I give an input here for this perceptron, oh, you cannot see that. When I give an input here for this perceptron, do you know the failed vector? We don't know. Okay, the labels are only for input to output. input to hidden is not known. Okay, only if you're able to decompose the non-linearly separable function into linearly separable functions, then you will know. But in general, it is not possible. For real life problems, you cannot decompose into linearly separable functions. So the level here is not known. And therefore, I have no notion of a failed vector. Okay, and similarly, for the outermost neuron, we do not know the input patterns which will be called failed or success. Okay, nothing is known about the hidden layer. So perceptron training algorithm will not work. Then we have to think of some other strategy. So this strategy again is one of the pillars of AI. It's the gradient descent rule. Gradient descent rule. So imagine the neuron M and the feeding neuron N. WMN is the weight connecting N to M. For the class, we follow a convention. The target neuron is closer to the weight. So WMN, M is the destination neuron, N is the source neuron. Please remember this notation. There shouldn't be any confusion. M is destination, N is source. Okay, so we are interested in knowing how to change this weight value W. Okay, so WMN is the weight of the connection from the nth neuron to the mth neuron. Now, error versus W surface is a very complex surface in the space defined by the weights Wij. Okay, so if you take this network, for example, the number of parameters are, that is number of weight values, and the thresholds are 3, 1, 2, 3. And the parameter values, weight values are 4 plus 2, 6. So 6 plus 3, 9 parameters are there. Okay, so in a 9-dimensional space, the error versus the weight value will be a very complex surface. So for every value of the weight for a given input, we find out the error value and plot it in that 9-dimensional space. So this will be a very complex surface. So our goal is to reduce the error, which is given an input, which is a function of the parameters. So E versus W surface is a complex surface in the space defined by the weights Wij and theta. So minus delta E minus delta W Mn gives the direction in which a movement of the operating point in the WMN coordinate space will result in the maximum decrease in error. Okay, so we consider the negative of the gradient delta E delta WMN. Okay, so as we change WMN, error also will change. So we are interested in finding out the direction in which maximum reduction in weight will take place. That will happen by minus delta A delta Wn. This is called the gradient descent rule. This is called the gradient. Now comes the rule. The rule that comes is this, that delta Wji, the change in weight, Ji, J destination, I source, is proportional to negative gradient, negative derivative of E error with respect to that particular weight. Okay, so this is the gradient descent rule for change of weight and is the starting point for the backpropagation algorithm. So the change in weight is equal to minus eta delta delta Wji. Eta is called the learning rate. Okay. Now there is a bit of algebraic manipulation for obtaining the expressions finally. But let's do this manipulation a bit. Delta E delta Wji is equal to delta E delta net J into delta net J delta Wji. Net J is the input at the jth neuron. Okay, jth neuron. Not layer, jth neuron. So j, let me do the correction. So we apply the chain rule of derivative. Delta E delta W Ji is equal to delta E delta net J into delta net J delta W Ji. Now delta E delta net J, okay, the derivative of the error, which is seen at the outermost layer, with respect to some neurons input, net J is the input at the jth neuron, is given a notation minus delta J. Okay, this is going to play an important role in the backpropagation. So delta WJI, which is the change in weight, is learning rate into delta J into delta net J delta WJI. Now delta net J delta WJI is equal to OI. Okay, why is it OI? So if you take, let's say, this neuron, then this neuron is receiving inputs from all the previous layer neurons. Okay, so the delta net J or net J is the input arriving in the jth neuron. And this is the dot product of the weight value and the input values. So this is sigma WJI into output from the previous layer neurons. So if you take this net input and take derivative with respect to WJI, it will be OI, the output of the ith neuron. Okay, so we have the universal rule of weight change in neural networks. Applies to deep learning, shallow learning, everywhere. This is called the universal rule of weight change. Delta WJI, where J is the destination neuron, I is the source neuron, is a very compact expression, is equal to learning rate into something at the destination neuron. It's called delta J, and something in the source neuron, the output of the source neuron. This is the universal rule for weight change in any neural network, whatever with the architecture, not necessarily feedforward, feedback neurons, recurrent neurons, everywhere this is the rule. And this is the rule which is responsible for Nobel Prize to an AI scientist, Jeffrey Hinton, this year. This is the rule. It is universal, widely applicable across networks, across domains, metallurgy, economics, computer science, electrical engineering, signal processing, everywhere one rule. Learning rate into something at the destination neuron into something at the source neuron. Any question? This derivation is very simple. Okay, simple differentiation and chain rules. So should be easy for you to see. Now we encounter some difficulties. Let's take this network. Okay. And if these are perceptrons, the computation neurons are perceptron, then a gradient descent rule will run into difficulty. Why so? I cannot apply gradient descent on these neurons. A network which is composed of perceptrons. I cannot run perceptron training algorithm. I cannot run, I cannot apply gradient descent. What should I do? Why gradient descent will not work? What is the answer? The input-output relationship for these neurons is not continuous. Before theta, it is 0. The derivative does not exist at theta. Sigma Wixi equal to theta. Okay, so for gradient descent, we need computing elements which have continuous input-output relationship. Okay, which are where the derivative exists for every point. And such neurons have been created. They are called sigmoid neurons. Okay, sigmoid neurons. I think sigmoid neurons are also logistic regression functions. So we'll talk about that. So what are the changes we made? Perceptron training algorithm will not work. We have to think of gradient descent. Perceptrons themselves will not work. So we have to take up sigmoid neuron. Now, the backpropagation algorithm works on multi-layer neural network, multi-layer perceptrons, feedforward network. So here is the outermost layer. This is the input layer. This is the outermost layer. This is the input layer. And the hidden layers are here. Okay. So you have to find out the weight change rule for each of these neurons. So let's see how it is done. Now the universal rule is eta delta j oi, which applies to every neuron in the network. Now see the definition of delta j. This is minus delta E, that is error, delta net J, the net input at the jth neuron. D is equal to minus delta E delta OJ into delta OJ delta net J. Again, chain rule. OJ is the output of the jth neuron, net J is the input of the jth neuron. Okay, so net J is the input at the jth neuron, and OJ is the output of the jth neuron. Okay. And the error is half into sigma p equal to 1 to m tp minus op square, where this p is going over the neurons. So for the outermost layer of neurons, it is easy to compute. Delta j is equal to minus tj minus oj, and delta oj delta net j is oj into 1 minus oj if the neuron is a sigmoid neuron. Okay, we are jumping the steps a bit. For the moment, just take my words that delta oj delta net j is oj into 1 minus oj. This is the derivative for what is called the sigmoid neuron. Okay, and then we get the change in weight as learning rate into tj minus oj, which is target minus observed, derivative of the sigmoid at the outermost at the destination neuron, multiplied by OI, output of the ith neuron. Okay. For hidden layer, it is little more complex because in the hidden layer, we do not know the error value. Error is known only at the outermost layer. Again, some kind of chain rule is applied, and we get the change in weight as backpropagated delta, sigmoid neurons derivative for the hidden layer neuron, and output from the source neuron. We'll derive this carefully in steps. So backpropagation rule gives me two different expressions for the outermost layer of neurons and the hidden layer neurons. Okay, and this expression is called the backpropagated delta. More about this as we go forward. Now let me take an application to show you how this backpropagation algorithm is applied and it has become so popular, okay, across various domains and applications. Let's see an application in medical domain. This is one of my favorite examples because it illustrates lots of fine points about backpropagation. So let's see what the problem is. The problem is that we need an assistant for a skin specialist. Okay, we need an assistant for skin specialist. So we are creating an expert system for skin disease diagnosis. So skin disease diagnosis is a difficult problem because of many complexities. We are creating an AI assistant for a skin specialist. Okay. Now, we know that in lots of countries, the medical professionals do feel a bit insecure about the advent of AI. Okay. Healthcare and medical is one of the most important consumers of AI technology now, AI science and technology. And in some countries, there is a bit of insecurity, thinking that AI will take the job, which by the way is happening. Okay. The interpretation of X-rays, CT scans is now done a lot with AI. In our lab itself, we have been working on automatic report generation from X-rays using AI. In India, the situation is different. In India, doctors are not threatened by AI. Doctors welcome AI. Doctors and medical professionals. We have been talking to lots of radiologists for our research. They say that we are extremely overburdened, cannot cope with the patient demand and the requirement of our work. We have to see umpteen number of X-ray plates throughout the day, and here a preliminary screening by AI will help a lot. But AI systems must be trustworthy, especially in things like healthcare, law, education. AI's decisions should be explainable and they should be trustworthy. So that has given rise to a very important field called responsible AI, where AI systems decisions should be responsible. So, this is the problem formulation. The skin condition is examined. Some of the observations are bumpiness and scaliness of the skin, mostly for symptom gathering and for developing the diagnosis skills. And the purpose is not to replace the doctors. Okay, the purpose is to assist them. And this is being done. It was a sponsored project for us long back from a company called Siemens, who are in medical domain quite a lot. So we decided to use feedforward neural network, and the configuration was 96-20-10. What is this 96-20-10? 96 input neurons, 20 hidden layer neurons, only one layer, and 10 output neurons. So 10 output neurons corresponding to 10 skin disease conditions. So the input is skin disease symptoms and their parameters, location, distribution, shape, arrangement, pattern, number of lesions, presence of an active noder, amount of scale, elevation of papules, color, altered pigmentation, itching, pustules, lymphadenopathy, palmar thickening, result of microscopic examination, presence of herald pathogen, I suppose, result of dermatology test called KOH. All these we as computer scientists could not have done. Doctors had to tell us. Okay, so you see how doctors are not replaceable. The input vector is decided by consultation with doctors who bring in the medical knowledge. Otherwise, we are groping in the dark. Okay, what should be the input? Then the 10 neurons are indicative of the diseases. The names are quite scary and interesting. Maybe psoriasis, pityriasis, rubra pilaris, lichen planus. I don't know what they are. Some of them I cannot pronounce also. Pityriasis, rosea, tinea, versicolor, dermatophytosis, cutaneous T-cell lymphoma, secondary syphilis, chronic contact dermatitis, psoriatic dermatitis. These are all Latin names, I suppose. And these also were told to us by doctors. Otherwise, we would not have known, okay, what are the diseases. And doctors also told us that out of these disease conditions, psoriasis is most difficult to isolate because it has lots of similarity with other disease conditions. Okay. And then by trial and error, remember trial and error, we first decided that we will have only one input layer. not more than one input layer. Though in today's deep learning systems, you have layers and layers and layers of neurons. In transformer, you have 6 layers in the input side, encoder side, 6 layers on the decoder side. Okay, and so on. So we decided only one layer, and the disease diagnosis will happen at the outermost layer with 10 neurons, 96 neurons in the input layer, 96 came from the doctors. And so the feedforward network is now a complete and pure feedforward network from input to hidden layer to output. Okay, and the outputs were given to us for the corresponding input conditions. The outputs were in the form of 1, 0 vectors. Okay, there can be multiple diseases, so more than one neuron can be on. There can be only one disease, so only one neuron is on. So this is a case where you have to use total sum square error. Okay, if only one disease was present at a time, then you could have used a probability distribution. Okay, the probability of psoriasis is 1, or probability of dermatophytosis is 1, others are 0. But many times it is a multiple disease condition, therefore multiple ones. So this is the hidden layer, and we train the system with the data given to us. Let's see some of the logistics. Input specs of 10 model diseases from 250 patients were given to us. 0.5 is some specific system value is not known. Okay. Trained using standard error backpropagation algorithm. So you see a very small number of data items, only 2,500. This is laughably small in today's deep learning systems. This was some 15 years back, 15, 20 years back. Nowadays, medical data are many times in 10,000, 100,000, sometimes millions also. Okay, and so the training algorithm has to be running quickly on powerful computing machines. So testing was done in the following way. Previously unused symptoms and disease data of 99 patients we had got. The result was this. Correct diagnosis was achieved for 70% of populous squamous group skin diseases. Success rate above 80% for the remaining diseases except for psoriasis. Psoriasis is diagnosed correctly only in 30% of the cases. Okay, and psoriasis resembles other diseases within the populous squamous group of diseases and is somewhat difficult even for specialists to recognize. Okay, even doctors get confused for psoriasis. Okay, psoriasis is mainly itching of skin. Okay, it's not a life-threatening disease, but mainly itching. Explanation ability. So rule-based systems reveal the explicit path of reasoning through the textual statements. If this was a rule-based system, then we would have got the path of reasoning and explained also the decision. Connectionist expert systems reach conclusions through complex, nonlinear, and simultaneous interaction of many units, which are the neurons. Analyzing the effect of a single input or a single group of inputs would be difficult and would yield incorrect results. Okay. The hidden layer re-represents the data. That is the most interesting part. And the outputs of hidden neurons are neither symptoms nor decisions. So that is the most interesting part of the discussion. And just remember, in the lab, you will have to probe the hidden layer, what the hidden layer is doing. So these neurons were doing something which we did not know. These neurons were producing diagnosis. These neurons were representing input. Hidden layer neurons, what were they doing? Okay. So some investigation revealed that these neurons were taking common attributes of 2-3 diseases and representing them. Okay, so the common factors contributing to psoriasis and dermatophytosis, they were represented in some of the neurons, which the probing revealed. But that probing was not really satisfactory. I do not claim that we got very insightful understanding of the hidden layer neurons. And you can imagine when you have millions of neurons and many thousands of layers, the neural network has to become a black box. You just cannot probe the neurons unless the neuron is close to the outermost layer. The outermost layer's behavior is known. And we hope that neural layers which are close to the outermost layer, their behavior also can be probed. So this was one exercise we did for a company, and they said that, okay, I mean, 70% accuracy for a certain group of disease is okay, but you have to go far. It is a healthcare situation, so accuracy really has to be high. Symptoms and parameters contributing to the diagnosis are found from the network. Standard deviation, mean, and other tests of significance used to arrive at the importance of contributing parameters. The network acts as apprentice to the expert. So this is an important point. This is called explainability. Now let's say psoriasis is the disease present. We observe many data points and see which symptoms are correlated strongly with psoriasis. Okay, so this can be probed from the input layer and its weight values. Okay, and then that corresponds to what is called explainability through correlation. Now, interestingly, we found that the medical community is not interested in shallow correlations and explainability. What they want is causal explanation. Causal. Okay. Can you tell me, by training a network, what causes psoriasis? What causes seborrheic dermatitis? Okay, so causal explanation. So explanations these days are very shallow. They are correlational. Okay, for psoriasis, I see that duration of lesion has a strong correlation. Fine, doctors say we know that. We know that from our analysis of, from our investigation of patients. But what are the causal relationship between duration of lesion and psoriasis? To give you an example, what do I mean? So suppose a person has jaundice. Okay. Now the color of skin, urine, eye, they become yellow. So color of skin, urine, and eye are three inputs. We will see strong correlation from the data. But that's not enough for the doctors. Doctors would like to ask, okay, jaundice because of this yellow color, but why does the yellow color happen? In case of jaundice, why do you have yellow color? In case of jaundice, the yellow color happens because an ingredient called bilirubin increases in the bloodstream. Okay, so the cause is bilirubin. But you can go further and ask, why does bilirubin increase in case of jaundice? That's further medical investigation. So you see, the community is very ambitious. They would like these AI systems to give that kind of explanation, going deeper and deeper. Lots of research can be done there. And some of these we are also investigating, helped immensely by doctors. In case of law also. Okay, so we have been working on consumer grievance redressal, where an AI agent will help them. And then the causal explanation there is, okay, this grievance is due to, let's say, the brake of a car malfunctioning. Then which rule of Consumer Act is applicable? Okay, that is something the AI agent should be able to tell us. So the ask is very high, and I hope you will think of your AI work from that point of view. Okay, then yeah. So so let me just go back to any question on the explanation. Why only hidden layer? We decided to go only with one hidden layer. That is by trial and errors. Now let's see how XOR network will work for backpropagation, just to ground our understanding of backpropagation. So the input propagation is forward and the error propagation happens backward. So we have trained a network and we have got these weight values. Okay, -1, 1.5, 1.5, -1, and so on. So when I give the input 0, 0 here, okay, I have initialized the weight values, let's say this way. When I give 0, 0, then these neurons will compute the dot product of W and X. And then pass this input through a sigmoid function. So the sigmoid function will produce a value between 0 and 1. Then we have another neuron here, which is also sigmoid. So, so that will again take the dot product of the weight values and the input values and pass it through a sigmoid. Now for 0, 0, we know that the output should be 0. And let's say we have got an output 0.7 because sigmoid's output is always between 0 and 1. So we have got a value of 0.7. So 0 minus 0.7 is my error. I'll take square of that, which will be 0.49. And that error will now be back propagated over these weight values, and the weight values will correspondingly change. And the hope is that by changing the weight values, we'll be able to reduce the error. Okay. The gradient descent rule is always has always this property. When we apply gradient descent and change the weight value, the error always decreases. So in that sense, the gradient descent algorithm is a greedy algorithm. It always decreases the error. And in greedy algorithm, you know the classic problem. In greedy algorithm, the main problem is that the system can get stuck in local minimum. So these are the nitty-gritties we'll go into, and we'll keep discussing this very important topic in AI. Okay, so today's slides, up to today's slides in this week will be uploaded. And the quiz syllabus is up to what has been done today. Just pay attention for 2-3 minutes. Remember that you have to be in LH101 and LH302. There will be only one A4 sheet paper. You have to write the answers on 2 sides of the A4 sheet paper, no extra sheet. Do any amount of rough work you can in the rough sheets, but post the neat and clean answer on the sheets. If your handwriting is bad and there is complete chaos on the answer book, it will be difficult for us to evaluate your answer. Okay, so have very neat posting on the A4 sheet of paper. Cheat sheet is allowed. You can bring one cheat sheet of anything that you want to write. Okay.